In previous lecture, we have discussed a very important concept which was actually Fermi surface. And you have seen that Fermi surfaces are actually a surface in K space along which the energy remains constant. In other words, you simply say that it is a surface of constant energy in K space or momentum space. And we have also learned how these Fermi surfaces are constructed. Actually, we have discussed two important methods for the construction of Fermi surfaces. You have seen what is the method of construction which is called a reduced zone method and the periodic zone method. But now it is time how to determine this Fermi surface in case of proper materials by experiment. Okay. So actually there are several experimental methods to determine the Fermi surface. And among those different experimental methods, one of the most important powerful method to determine the Fermi surfaces of materials like metals and semiconductors is cyclotron resonance method. So you can say that cyclotron resonance method is a powerful experimental method for the determination of Fermi surfaces. Okay? And our aim in this lecture is to discuss the basic principle of this cyclotron resonance. And after this lecture on cyclotron resonance, which will be regarding the basic principle of cyclotron resonance, we will separately learn about the determination of Fermi surface for metals and semiconductors. Okay? Actually, when you say that we have to determine Fermi surface of a particular material, what does it mean? Actually, determination of Fermi surfaces means determination of effective mass of the current carriers in that crystal. Because the effective mass is directly related to the EK curve. Because in the definition of effective mass you have seen that this effective mass is defined as 1 over M star is equal to 1 over H bar square d2E by dk square. This is the definition. This M star is actually the effective mass. So, how E is related to K? That energy versus K relation actually determines the effective mass of the charge carrier, and that EK curve also decides the Fermi surface. So the problem of determining Fermi surface is same as the problem of determining the effective mass of the current carriers in crystals. Okay? And you can say that it enables us to determine the shape of constant energy surfaces of the conduction and valence band near the band edge. Or you can say that it determines the EK relation, that is energy versus K relation, that can be determined by this cyclotron resonance method. Okay? So this cyclotron resonance method also provides, you can say, the experimental evidence for the band structure in crystal. Okay? So what is this cyclotron resonance, when it takes place, and what is its basic principle? All these things we will learn in this first lecture on cyclotron resonance. And as I have told you earlier, that after this video, we will have at least 2 videos on this cyclotron resonance, and those will be related to the determination of Fermi surfaces of metals and semiconductors using this cyclotron resonance method. Okay? But let us now start to know what is this cyclotron resonance. In this regard, I would like to say you, definitely you have studied a particular particle accelerator called cyclotron. Actually, in the device cyclotron, which is a particle acceleration which is used to accelerate heavier ions, okay? Definitely you have seen that the heavier ion revolves along a spiral path under a constant magnetic field, and an alternating electric field is also applied which actually accelerates the particle and increases its velocity so that its radius of the orbit followed by the ion increases, and it finally follows a spiral path. Actually, that principle is used in this experiment, so it is called cyclotron resonance. Why it is called resonance, we will also learn it. In fact, when you talk about cyclotron resonance, in this case, the charged particle, just like electron or ions, move in a circular or helical path in presence of a static and a strong magnetic field. A static field means constant field. Okay? As you can see in this figure, I have shown here that a particle of charge Q is revolving along a circular orbit of radius r in a static magnetic field which is B, or its intensity is H. Actually, this has been shown that if you assume that this plane in which the particle is describing this circular orbit is XY plane, let us say, then a magnetic field H or B is applied perpendicular to this XY plane, and you can say that the magnetic field is along the Z axis. This cross sign actually represents the sense of the magnetic field, which represents this is into the plane or into the page. Okay? That is in negative Z direction here. Actually, due to this magnetic field, a centripetal force, a magnetic force or Lorentz force acts on the particle. And that Lorentz force acts like a centripetal force, and it provides circular motion to the particle. Okay? Now, if you consider that H is the intensity of magnetic field, okay, and V is the velocity of the charged particle revolving along this circular orbit, what will be the equation of motion? How this circular motion is possible? Because I have told you that this force F, which acts toward the center of the orbit, this is simply the magnetic force acting on the particle. And that force acts like a centripetal force and provides circular motion to the particle. Okay? In fact, in this condition, we will also apply an alternating electric field. In experiment, particularly in this case, we use a circularly polarized radio frequency electric field, okay, in the plane of the orbit. And that electric field is applied in such a manner that the force applied by the electric field QE on the charged particle acts parallel to the direction of velocity of the particle. So that due to this alternating electric field, the velocity of the particle increases, and when velocity increases, the radius of the orbit also increases. Okay? But this electric field is not a constant field, but this is in fact alternately varying electric field. E is given as E naught e to the power I omega t. Here I stands for iota. Okay? And actually it is seen that when this electric field will be applied, actually this charged particle absorbs energy from this electric field. Okay? And when the frequency of the rotation of the particle, which is omega c. This is called cyclotron frequency actually. So omega c, which represents the frequency of revolution of this charged particle, when it is equal to the frequency of the applied electric field, then the energy absorbed by the particle from the electric field is highest. This is maximum. And this phenomenon is called resonance. Okay? So this frequency omega c, at which our particle absorbs maximum energy from the alternating field, that frequency is called resonant frequency. Okay? And this phenomenon is called cyclotron resonance, because such a situation occurs in the particle accelerator cyclotron. So taking an analogy from there, it is called cyclotron resonance. Okay? Actually, we will see that by the knowledge of the magnetic field H which we applied the condition omega c equal to omega for the cyclotron resonance, from these informations we will see later on we can determine the effective mass of the charge carrier M star. Okay? And once you know M star, you can find the energy versus K relation. It means you will be able to find the Fermi surface. Okay? So this experimental arrangement is also known as effective mass spectrometer. This is called effective mass spectrometer. Okay? For your convenience, actually I have written here all those things which you have just explained. Okay? And as I have told you earlier that this cyclotron resonance is used in determination of the effective mass of current carriers in crystal, and it is also used to determine the Fermi surfaces. Okay? But first of all, we will like to find the cyclotron frequency. Okay? And for this you can see, as I have told you, that when a charged particle of charge q is revolving inside the crystal along a circular orbit under the static magnetic field H, then what will be its equation of motion? Actually, magnetic force applied on acting on this particle due to the magnetic field acts like a centripetal force, and so you can write its equation of motion in this way. This is the force, because you know the magnetic force is given as, if Fm is the magnetic force, this is given as Q times V cross B. Okay? Q times V cross B. Here you can see that motion is of this particle takes place in this plane, but the magnetic field is perpendicular to the plane. So actually these two vectors V and B are perpendicular to one another. So angle between these two is 90 degree, and therefore magnitude of magnetic force will be simply QVB sin 90. Okay, QVB sin 90, but sin 90 is 1, so this will be QVB. Okay. Here I have assumed that the charge carrier has a charge E. So instead of Q we will write E. Okay. And here I have also used the sign of plus minus. Why this sign of plus minus has been used? The reason is that when you project two charge carriers like electron and hole, you know electron has negative charge and hole has positive charge. And if a negative charge and a positive charge is subjected to the same magnetic field, the sense of rotation of both charges will be just opposite to one another. If you consider that electron revolves in anti-clockwise sense, then in that magnetic field, the positively charged hole will revolve in clockwise sense. So, since the charge carrier in crystals may be either positively charged hole or negatively charged electron, so for those, this plus minus sign has been used. Okay, I think you have understand why this plus minus sign is used. So in SI unit, you can write the equation of motion like this. This is plus minus BeV equal to m star V square divided by R. You know, this m star is what? This is effective mass of electron. Why you have taken effective mass instead of the free mass of electron m? Because here we are talking about the charged particle which is not free, which is inside the crystal. And you know, you have studied in band theory that we can write expression for band theory simply replacing m by m star. Okay. So as we are talking about the charged particle inside a crystal, so instead of the free mass of the charged particle m, we will have to write m star, which represents its effective mass. So this is the equation of motion of the charge carrier in SI unit. But here we will make our calculation in CGS unit, or you can say in electrostatic unit. So when charge of this carrier E is measured in electrostatic unit ESU, and instead of this magnetic induction B, we use the magnetic intensity H, which is measured in oersted, then the magnetic force is given by HeV over C, okay, where C is speed of light in free space. And so this will be equal to m star V square over R. And from here you can see one of the V in both sides will cancel out, and therefore R will be equal to m star V over He times C. This is the expression for the radius of the orbit. And you can see from here that this radius is directly proportional to the speed of the charge carrier. So whenever a speed of the charge carrier increases by any region, the radius of the orbit will also increase in same proportion. Okay? So particle of different speed will move along orbits of different radii. Okay? So this is the expression for radius of the orbit, which we have obtained simply by writing the equation of motion of the charge carrier. Okay? Now, if you want to find what will be the time taken by this charge carrier in making one revolution, let us say that particle starts from this point P and moves along this orbit and again returns back to this point P. This is called one revolution. And time taken in one revolution is called period of revolution. How you can find it? Since along a particular orbit, the charge carrier moves with a constant speed. So if your aim is to find the period of revolution, that is time taken in making one revolution, then how you will find it? What will be the distance covered in one revolution? That will be simply equal to the circumference of this circle. So distance covered in one revolution will be 2 pi r. Okay? And if t is the time taken in describing this distance, how you will find t? You will simply divide this distance by the speed, because the speed is here constant. So time taken in one revolution, that is period of revolution of this particle, is 2 pi r over v. Okay? And so this will be 2 pi over v times r, and r is this much. Okay? Now this v and this v will cancel out, and you can see that time period is this much. This is 2 pi m star c over h. Okay? And you can see that this time period is independent of v. It is not a function of v. So t is proportional to v to the power 0. It is independent of v. It means time period of revolution of different charge carriers or a charge carriers revolving along different orbits will be same. Okay, it will be same. Once you know the period of revolution of the charge carrier, you can easily now find what will be the frequency of rotation of this charge carrier. So angular frequency of rotation of the charge carrier will be equal to 2 pi over t. Okay, 2 pi over t. So this is 2 pi, and what is t? Let us put the value of t from here, and you will get that this is 2 pi times He over 2 pi M star C. And you can see this 2 pi and 2 pi will cancel out, and so the angular frequency of the charge carrier is omega c, and this is Eh over M star C. Actually, this frequency is known as cyclotron frequency. This is called cyclotron frequency. And as I have told you earlier, when you apply the alternating electric field in that plane in which this particle is moving in such a way that the field is being parallel to the so that the force exerted by the field is parallel to the direction of the charge carrier's motion, and so that it accelerates them to the higher energy and enlarge their orbits, exactly as in case of cyclotron particle accelerator occurs. Okay, so the absorption of energy from the radio frequency field is greatest if the frequency of this field omega is equal to this omega c. Then the charge carrier absorbs maximum energy from the radio frequency field, and this event is known as cyclotron resonance. Okay, cyclotron. But what will be the criteria for observable absorption of energy from the oscillating field? Now we will learn about it. It may, as you have seen, that resonance will take place when frequency omega of the alternating field is equal to the cyclotron frequency. Okay, but when omega is equal to omega c, then how you can say that the maximum energy will be absorbed by the particle, and what will be the criteria for this maximum energy absorption? Okay. In fact, there is a problem here. The current carriers constantly suffer collision as they move about inside the crystal. You know, the charge carrier, either electron or holes, will suffer collision with the ions of the crystal. Okay, and if they collide, then during that collision, the charge carrier will be stopped. Okay, and that the time of that will be unable to absorb the energy from the field. Okay, because when the charge carrier collide with the ion, then after every collision they will return to their initial energy. Okay, however, it turns out from the but a particular analysis which we will just now follow, that there will be a particular condition under which, or when that condition will be satisfied, then it is found that there is an observable absorption of energy. And what is that condition? We will see that when omega times tau is greater than 1. What is this tau? This tau is called relaxation time, and you have learned about this relaxation time when I have discussed the Sommerfeld theory of electrical conductivity and thermal conductivity. Actually, this tau is the average time taken between two successive collisions. Okay, so when this criteria will be satisfied, omega times tau will be greater than 1, then you will see that there will be an appreciable absorption of energy and resonance will take place. Okay, But how we can say this? For this we will now see the mathematical calculation from which we will be able to show that the criteria for the observable absorption of energy is omega tau must be greater than 1. Okay? And for this, let us consider that our charge carrier is moving inside the crystal and Vd is its drift velocity. E is the charge of the carrier, capital E is electric field and capital H is magnetic field. Okay? Then we will write the equation of motion of this charge carrier. You know, equation of motion means we will apply the Newton's second law of motion. And according to Newton's second law of motion, mass times acceleration will be equal to net force acting on the particle. So here, mass, at the place of mass, you have to write m star because you are not talking about a particle in free state. It is inside a crystal. And if it is inside a crystal, you should take its effective mass. Okay? You have already discussed this thing. So m star times dv by dt, this is its acceleration. That will be equal to net force. Now, what forces are acting on our particle? One of the force is electric force, which will be E times capital E. Another force is magnetic force, that will be E times Vd cross H over C. And apart from this Lorentz force, a force due to collision is also experienced by our charge carrier. That force is actually called viscous dragging force. Okay? That is a force of friction or viscous dragging force, and that force is given by m star Vd over tau. This is viscous force. And this force acts just in opposite direction of the Lorentz force, because this viscous dragging force opposes the motion of the particle. So I have put it here minus sign instead of plus sign. So the equation of motion is given as m star times dvd by dt equal to E times capital E plus Vd cross H over C minus m star Vd over tau. Okay? And as I have told you that this tau is relaxation time, which is actually the average time between two successive collisions. And m star times Vd over tau, this is the measure of viscous dragging force due to collision. Okay? Now for simplicity, we assume that the alternating electric field which we have applied on the charge carrier is directed in x direction. So you can write vector E is equal to EI. But the magnitude of this electric field vector is not constant. It varies alternately with time, and it is given like this: E equal to E naught times exponential to the power iota omega t. Okay? But the applied magnetic field is a static, that is constant, that is not alternating field. So H is constant and I have applied it in z direction. Okay? So H is directed along K. Okay? Now we can see a very important operator in a particular form. You can see this equation, E equal to E naught e to the power I omega t. So from here you can find dE by dt, and that will be I omega times E naught e to the power I omega t. But see, E naught times e to the power I omega t, this is simply E. So dE by dt is equal to I omega operated on E. So here the function E in LHS and RHS are same. So you can say that the operator d dt is just equivalent to I omega. Okay? So operator d dt is equivalent to operator omega, I omega. Note, omega is a physical quantity, but I omega is not a physical quantity, but it is an operator. So now, using this idea of new operator for d dt, Okay, and we will write this equation of motion in component form, in a scalar form. And for writing this equation of motion in a scalar form, we will have to express all the vectors in terms of their components. So let us see what will be this Vd cross H. Vd cross H exists here. You can write this Vd as Vxi plus Vyj plus Vzk. Here Vx, Vy, Vz are the x, y and z components of the drift velocity Vd. But H is simply equal to Hk in accordance with our assumption. Okay. So let us now find the cross product. You know, I cross k, this is minus j. So I have put it here minus sign and this is j. And the remaining factors will be Vx times H. So the first term is minus Vx times Hj. Okay. And now j cross k, that is equal to I. So the second term will be Vyhi. But k cross k is 0. So last term has been not written here. Okay. Now in terms of components, how you can write this equation of motion? Write it. See here, M star. Okay. Actually, one thing I have done here. Actually, this second term in RHS has been now brought into LHS, because both of these terms in LHS and RHS contain M star. So you can combine these two terms and take this M star as a common factor. So M star has been taken as a common factor, and at the place of this dVd by dt, for the operator d dt, you can write I omega, and for Vd, we will write this much. Okay. And plus M star has been taken constant. For Vd, now you can write Vxi plus Vyj plus Vzk and divided by 2. Okay. Now you know, if two vectors A and B are equal, any two vectors, then what happens? If two vectors are equal, their corresponding components are equal. It means if F is equal, if A is equal to B, Ax will be equal to Bx, Ay will be equal to By, okay, and Az will be equal to Bz. Okay. So now you can equate the x component of the vectors in LHS and RHS, similarly y components of the vectors in LHS and RHS, and so that this vector equation will be splitted into two scalar equations. So let us now write the equation for x component. See, this is M star, and I is present here and also here. So these two terms will be for the x component in LHS. So this will be M star times I omega plus 1 over tau times Vx. Okay. And in RHS, these two terms are for the x component. So this will be E times E plus Vy times H over C. Okay. Now for y component, see the y component in LHS. Here the term containing j is present, and here also j is present. Okay. So this will be M star times I omega plus 1 over tau Vy, and that will be equal to, now only one term containing j is in RHS, so this will be equal to minus E Vx H over C. So this vector equation has been splitted into two scalar equations. Now for a z component, you can see there is no term in RHS, so that will be equal to 0, so and that I have not written here. Now for simplicity of calculation, we consider that this 1 plus I omega t is equal to A. We consider it, we assume it. When we will get the final result, again we will replace this A by this much. Okay. And here you can see there is term I omega plus 1 over tau. When you will take actually LCM, this will be tau and I omega tau plus 1. So this will be in our calculation, and for that I have assumed A. When you will take this much equal to A, then what will be this equation 4 you can see. Then Vx will be equal to this much. This will be E times E plus Vy H over C times tau divided by M star A. You can check it. Okay. Now in the expression for Vx, you can see Vy is contained in RHS. Now find the value of Vy from this equation 5. You can find it. From that equation 5, Vy will be equal to this much. You can check. This will be minus E over C H tau Vx over M star A. Okay. Now we will substitute this value of Vy in the equation for Vx at the place of this Vy. Okay. So after substituting this, you will get that this Vx is equal to E tau over M star A. Actually, I have divided the denominator, the two terms in numerator separately by this denominator. So the first term will be E tau over M star A, and in second term this will be E tau H over C times M star A at times Vy. But Vy, you can see this is this much. So at the place of Vy, I have written this. Okay, this is at the place of Vy. Now let us simplify it. You can see that this Vx will be equal to E tau over M star A minus, now see here, this will be E square over C square, okay, times tau square H square over M star square A square times Vx. Okay. Now bring this second term containing Vx in LHS, and already Vx is present in LHS. So take this Vx as a common factor, and your result will be Vx times 1 plus E square over C square times tau square H square over M star square A square, and that will be equal to E tau over M star A. Okay. And so now you can easily find what will be this Vx, taking this M star A star as LCM here. Okay. So you can see this Vx times M star A square plus E square over C square tau square H square over M star square A square, and that is equal to this much. Okay. Now this M star A and this square will cancel out. Okay, and so Vx will be equal to E tau times M star A over this much. Okay. Now take this M star square as a common factor in denominator. Okay. Then in the denominator, the remaining factor will be A square plus E square over C square tau square H square over M star square, because the second term does not contain M star. Now this M star and this square will cancel out. Okay, and so you can say this Vx is equal to E tau times A over M star. Okay, and divided by A square plus E square H square over M star square C square times this much. Okay, and see here, this is nothing. Okay, now you can see the quantity EH over M star C. You have calculated earlier that this is omega C, which is called cyclotron frequency. So instead of this EH over M star C, you can write omega C, and your result for Vx then will be like this. This is E tau times A over M star over A square plus omega C square times tau square. Okay, this is the expression for Vx. Okay, now as the electric field has been applied in x direction and we are talking about the velocity of the charge carrier also in x direction. Okay, so due to this drift motion, actually current will be constituted in x direction. Okay, and our aim actually is to find that current or current density, and for the calculation of that current density you need the value of Vx. Now as you have I have told you that this A is equal to 1 plus I omega t. Now after getting the result for Vx in terms of A, now we will substitute its original value. So now put 1 plus I omega tau instead of A, and so expression for Vx will be E tau over M star times 1 plus I omega tau and divided by A square, and A square means 1 plus I omega tau whole square, and you can simplify it by the formula A plus B whole square, which will be A square plus B square plus 2AB. So this will be I omega square tau square. I square is minus 1, so this is minus omega square tau square plus this 1 square, so this is 1, and 2I omega tau, and the second term is, remains at ease. This is the second term. Okay. Now in first term and last term in denominator, this tau square is a common factor. So you can write Vx equal to E tau over M star times this much over 1 plus omega C square minus omega square tau square plus 2I omega tau. So this is the velocity of the charge carrier in x direction, or you can say the drift velocity in x direction. So if n is the number of charge carrier in unit volume, or you may say that this is charge carrier density, then you know the current density in x direction will be Ne times Vx. Ne times Vx. But according to the macroscopic form of Ohm's law, you know Jx is given as sigma times Ex. Okay? But Ex in the present case, you know, is equal to E, because electric field has been already applied in x direction. So the complete electric field is equal to its x component. Okay? So Jx is equal to sigma E. And now you can find the electrical conductivity of this material, and that will be equal to Jx over E. And Jx is NeVx, so this is NeVx over E. Now let us substitute the value of Vx which you have obtained here. Okay? So after substituting this value, sigma will be equal to Ne square tau over M star times 1 plus I omega tau over 1 plus omega C square minus omega square tau square plus 2I omega tau. Okay? Now remember, when you have studied the Sommerfeld theory of electrical conductivity of metals in free electron theory of metals, what you have learned about the electrical conductivity? In actually, according to free electron theory of metals, the electrical conductivity of metal is given as Ne square tau over M. Okay? And in that theory, you have assumed that we apply a constant electric field over the metal, not a time-dependent magnetic field, not an time-dependent alternating electric field, not but only a constant field was applied. And when a constant electric field is applied, then you have obtained this result. Okay? So can you say, if we are talking about the band theory, then what will be the electrical conductivity of the metal? Okay? When the static electric field is applied, answer will be Ne square tau over M star. This will be the expression for electrical conductivity of metal in accordance with band theory when electric field will be constant. Okay? But when the electric field is not constant, but it alternately varies with time, or you can say that electric field varies with a frequency omega, then what will be the expression that has been obtained here? So this result, sigma equal to Ne square tau over M star into 1 plus I omega t tau divided by 1 plus omega c square minus omega square tau square plus 2I omega tau. This is the expression for electrical conductivity of material when we apply the alternating electric field, not a static electric field. Okay? And this will be the expression when this field will be static, and we will write the expression in accordance with band theory, and this is the result in accordance with free electron theory. Okay? I think everything is now clear to you. So this Ne square tau over M star is denoted by the symbol sigma naught, and this is called ordinary or DC conductivity of the solid at omega equal to 0 and also H equal to 0. When omega 0, it means you are talking about a static electric field and no magnetic field has been applied. Then this is the expression. But when you apply the magnetic field and an electric field which varies alternately with time, then the expression is for electrical conductivity is different, and that is sigma equal to sigma naught times 1 plus I omega tau over 1 plus omega c square minus omega square tau square plus 2I omega tau. And you can see from this result that actually the electrical conductivity of materials is a complex quantity. Okay? So this result shows that the high frequency conductivity is complex. Okay? And we can actually separate any complex quantity into its real and imaginary part by applying an appropriate algebra. So when you will apply an appropriate algebra to find the real and imaginary part of this complex quantity, what you will get? I have not done that mathematics, you can try it. And so the real part of the electrical conductivity is denoted by the symbol sigma r, and that is equal to, that will be sigma naught into this much. So sigma r over sigma naught is equal to 1 plus omega square tau square plus omega c square tau square over 1 plus omega c square tau square minus omega square tau square whole square and plus 4 omega square tau square. Okay? 4 omega square tau square. Now actually we will plot this sigma r over sigma naught in against of omega c over omega, because you can see the value of sigma naught is constant. Sigma naught is constant, but sigma r depends on omega. So varying the frequency of the applied radio frequency electric field, we can change the electrical conductivity of the material, or in other words you can say the electrical conductivity of material depends on the frequency of the applied field. Okay? So this is not the electrical conductivity in case of a static field. This is the electrical conductivity in case presence of constant magnetic field but alternately varying electric field. And this electrical conductivity depends on omega. So how this sigma r depends on omega? For this, when a graph is plotted between graph of sigma r by sigma naught is plotted in against of omega c by omega, then for different values of omega into tau, a different curves are obtained. And which curves will be obtained for what value of omega tau, you can see in this figure. Actually, we can see this first curve is obtained when omega tau is equal to 10. And you can see when this omega c by omega is equal to 1, it means omega c is equal to omega. That is in case of resonance. This sigma r by sigma naught is maximum. It is highest. Okay. So absorption of energy from the electric field is highest when omega c is equal to omega. Then absorption is highest. Okay. Again in second curve you can see when omega tau is equal to 2, then again it is found that for omega c equal to omega, the maximum value of sigma r by sigma naught occurs, which actually implies that there will be a maximum absorption of energy. Okay. And for omega tau equal to 1, you can see the same fact. But when omega into tau is 0.2, then you can see this point, let us say P, does not correspond to the maximum value, because at this point, and at this point, the value of sigma r by sigma naught is greater than that of corresponding to the point P. Okay. So it is clear that there will be the maximum absorption of power when cyclotron resonance takes place. And when cyclotron resonance takes place, then definitely this product omega into tau is greater than 1. Omega into tau is greater than 1. Only this omega c by omega is equal to 1 and maximum value of sigma r by sigma naught occurs, and that actually corresponds to the maximum absorption of energy. Okay. So when resonance takes place, then our charge carrier absorbs highest energy from the applied radio frequency electric field. Okay. And all these things I have written here. You can see the figure shows the graphical plot of sigma r by sigma naught in against of omega c by omega. It is clear that resonance takes place for omega tau greater than 1. You can see. And for larger value of omega tau, resonance is sharper, and hence there is an observable absorption of energy from the oscillating field when omega tau is greater or equal to 1. Then actually there will be the larger observable absorption of energy. Okay. So you can see that resonance is sharper when omega tau is large. As the value of omega tau increases, resonance becomes sharper and sharper. But if omega tau is less than 1, it becomes flat. Okay. It is not sharper. Okay. So this was the basic principle of cyclotron resonance, and I hope definitely you have understand every concept clearly. But as I have told you, in our forthcoming lecture we will see the actual experimental method for the determination of Fermi surface of metal and semiconductor. Okay. Thank you very much.